Hey guys, Mr. Backerberg here. In this video, we're going to look at the rectangular approximation method. Now, not every graph is nice and straightforward as far as finding the area underneath the graph. So in this example, we're going to look at something called a rectangular approximation method. And there's actually three different methods that we can use. So the function we're going to look at is the equation y equals x squared, and we're going to try to approximate the area underneath that curve from the x value of 0 over to the x value of 3. Now we know that if we were to graph out y equals x squared, then that would give us a parabola shape, but we're just going to look at x values between 0 and 3. So we're really just going to be looking at a small chunk of this graph and trying to approximate the area underneath our parabola. Now there's actually three different methods that we can use, and we'll look at breaking down each one. This first method that we're going to use is called a left endpoint rectangular approximation method. We can abbreviate that as LRAM. That means left endpoint rectangular approximation method. And what we're going to do is draw in some rectangles underneath our curve between the x values that we're looking at. Now in this example, what we're going to do is break our graph into 6 sub-intervals, but the more sub-intervals you use, then the more accurate your final answer will be. And we'll look at that later. But here, we're just doing 6 sub-intervals. So there's an interval that goes from 0 to a half, from a half to 1, 1 to 1.5, 1.5 to 2, 2 to 2.5, and 2.5 to 3. And each one of those rectangles has a specific width and has a specific height. And if we know the width and the height of that rectangle, then we can calculate each area individually and then add up all those areas. Now, because we're doing 6 subintervals going from 0 to 3, that means that the width of each one of these rectangles is going to be a half. So this width is a half, this width is a half, this one's a half. All of these rectangles have a width of 1/2. Now we can see as we move to the right, our rectangles get taller, and to figure out how tall these rectangles are going to be, what we're going to look at is the actual y value of the function for each of these x values. Because we're talking about endpoints on the function itself, then the height of each rectangle will correspond to that y value. So over here, we're starting at an x value of 0. Now, to find the height of that rectangle, I would take 0 and plug it into my function. And if I take 0 squared, I'm going to get a y value of 0. So as we look at calculating the area of this first rectangle, we know that its width is 1/2, and we know that its height is 0 from that y value. So that's going to give us an area of 0 for that first rectangle. Now if we look at our next x value, well, we said each of these rectangles was half a unit wide, so this next x value is at a half. And if I plug a half into my y equals x squared function, then I get a y value of 1/4. So taking a half times a fourth, that rectangle is going to give us an area of 1/8. Then if I go another half unit over, now we're dealing with an x value of 1. And if I take 1 and square it to figure out the height of that rectangle, then I'm going to get a y value of 1. So again, the width of the rectangle is a half. We just got a height of 1. So that rectangle gives us an area of a half. Then if we look at our next x value over, now we're at an x value of 1.5. And again, to figure out the height of that rectangle, I plug it into the function. It's y equals x squared. That's going to give me a y value of 2.25. So we've got a bottom width of 1/2 and a height of 2.25. So that's going to contribute an area of 1.125. Okay, so that was our fourth rectangle. We've got 2 more rectangles to do. So we're another half over. So now we're at an x value of 2. And if I plug that into my function, that's going to give me a y value of 4. So again, the bottom width of our rectangle is a half. The height we just came up with was 4. Half of 4 gives me an area of 2. Our last x value here is at 2.5. And to find the height of that rectangle, again, we're going to square that. So that's going to be 6.25. So then the base width is 1/2. The height is 6.25. So that's going to contribute an area of 3.125. So now to figure out the total area underneath this curve, we're going to add up all of those individual areas that we just found from all of our rectangles. And if I go ahead and add all of those blue boxed numbers together, I get an area of 6.875. So we're guessing that the area underneath this curve using these left endpoint approximation rectangles is going to be about 6.875. But what I want you to notice is as we're looking between these x values of 0 and 3, there's a lot of space that isn't getting accounted for. There's all of these individual chunks in here where our rectangles didn't quite reach up high enough to account for those. So in this instance, this LRAM is actually an under approximation because we're missing some of that area. Now, the next type of rectangular approximation that we're going to look at is called a midpoint rectangular approximation. So we're going to abbreviate this as MRAM. And we're approaching things very, very similarly. We're drawing in rectangles underneath our curve, and we're going to use the area of each rectangle to help us approximate the area underneath the total curve. So again, we're using 6 rectangles in here. So each of these rectangles is going to have a width of 1/2 again. But now as we're looking at where these points are on the curve, it's going to be the midpoint of each of these rectangles. So for example, if this first rectangle is 1/2 unit wide, and we look at the midpoint, well, the middle between 0 and 1/2 would be an x value of 1/4. Again, to find the height, just like we did before, we're going to have to plug that x value into the function itself. So if I take 1/4 and square it, then I'm going to get a y value of 1/16. Now, to find the area of that rectangle, just like we did before, we're going to take that width of 1/2 and multiply it by that height of 1/16. So that's going to contribute an area of 1/32. Now, this next rectangle goes between 1/2 and 1, so that midpoint there would be an x value of 3/4. And if I plug that into my function to find the height of that rectangle, squaring the top and the bottom of that fraction, I would get 9/16. And again, to find the area contributed by that rectangle has a width of 1/2, and it's got a height of 9/16. So that rectangle is going to contribute 9/32 to our area. If I look at my next rectangle, that runs between 1 and 1.5. So the midpoint there is going to be an x value of 1.25. If I plug that into my function to find the height of that rectangle, squaring 1.25, I get 1.5625. Now finding the area, again, we've got a width of 1/2, and we've got a height of 1.5625. So if I multiply those together, I'm going to get an area, I'm going to use decimals here because that's going to be easier, of 0.78125. Now my next rectangle runs from 1.5 to 2, so that's going to be an x value of 1.75, so 1.75. If I plug that into my function and square it, that's going to be a y value of 3.0625. And then again, to find the area of that rectangle, I'm going to take the width of 1/2 and multiply by that height of 3.0625. And if I type that into my calculator, I get an area of 1.53125. And I'm starting to run out of room a little bit in here. I'm going to box some of these areas so that I don't lose those answers anywhere. I've done 4 of my rectangles, so now I'm on to my 5th rectangle. This rectangle happens between the x values of 2 and 2.5, so the midpoint would be 2.25. If I take 2.25 and plug that into our function and square it, that's going to give me a y value of 5.0625. So now calculating the area of that rectangle, again, we've got a base width of 1/2 times that height of 5.0625 that we just found. And if I multiply those together, I'm going to get an area of 2.53125. So I'll box that so that I don't lose it. I've got one more rectangle to take care of. So that goes from 2.5 to 3. So halfway in between there would be an x value of 2 3/4. Plugging that into my function and squaring it, that's going to give me a height or a y value of 7.5625. So then one more area to calculate. I have to do 1/2 times that 7.5625. And if I multiply those together, that's going to give me an area of 3.78125. So that's my last area that I'll need. Now I need to take all of these individual answers and add them together. Now I typed all of those into my calculator, and that gives me an answer of 8.9375 using those midpoint rectangles to approximate the area. Now, in general, using these rectangular methods, your midpoint rectangular approximation method is going to give you the closest answer out of the three, because if we look at what's happening with each individual rectangle, like this middle rectangle in here, has a little bit of overestimation in it, but it's also got a little bit of underestimation in it. So those generally outweigh each other. So again, the midpoint is going to give us the most accurate out of our three methods. Now, if we look at our last method, this is called a right endpoint rectangular approximation. And what I want you to notice before we even get started on here, all of these rectangles have some overestimation on it. So because we've got some of our rectangles overhanging our graph here, we're going to get an overestimation. Again, we're going to use these 6 intervals in here to help us approximate the area. So this has a width of 1/2. All of these rectangles have a width of 1/2. And again, we're going to take these x values for these right endpoints, and we're going to have to plug those into the function to figure out the height of each rectangle, calculate the height of each rectangle, and then add all of those areas together. So for this first rectangle, because we're doing a right endpoint and each rectangle is 1/2 a unit wide, then we're going to look at an x value of 1/2. If I take 1/2 and plug that into my function and square it, I'm going to get 1/4 as that first height. Now taking our base width of 1/2 and multiplying by our height of 1/4, that's going to be an 1/8. Now the second rectangle has its right endpoint at 1, since each one of these is spaced 1/2 over. So that's an x value of 1. Plugging that into our function, we get a y value of 1. So then if we take our base width of 1/2 times that height of 1, that's going to contribute an area of 1/2. This next right endpoint is at an x value of 1.5. And if I take 1.5 and plug that into my function and square it, that gives me a height of 2.25. So taking that base width of 1/2 and multiplying by 2.25, that's going to give me an area of 1.125. Now I'm going to start boxing these areas before I lose any numbers. My next right endpoint is going to be at an x value of 2. If I plug that into my function and square it, that's a y value of 4. So we take our base width of 1/2, multiply by the height of the rectangle, which is 4. 1/2 of 4 is 2. And again, I'll box that so I don't lose that number. My next rectangle has its right endpoint at 2.5. If I take that and plug that into my function and square it, 2.5 squared is going to give me a y value of 6.25. So taking that base width of 1/2 times 6.25 is going to give me an area of 3.125. And again, I'll box that so I don't lose it. My last rectangle has its right endpoint at 3. And if I plug that into my function, that's going to give me a height of 9. So I'll do 1/2 times that height of 9, which is going to give me 4.5 as the area of that last rectangle. And one more time, I'm going to take all of those individual areas and add them all together using my calculator. And that's going to give me an area of 11.375. Now, we already talked about this one being an overestimate because our rectangles have some chunks that are hanging over the top of the graph, so all of those shouldn't technically get counted in the area. Our first one, the left endpoint, was an underestimation because we had some areas not being counted, and we said that our midpoint was going to be the most accurate out of the three methods because if we look at the part that's overhanging our graph versus the part that's not getting counted, they almost cancel each other out. Now, that's a really long and tedious process, even just using 6 rectangles to help us approximate the area. And I said that the more rectangles you use, the more accurate your answer is going to be. So when we used 6 rectangles, here's the numbers that we came up with for our left endpoint, our mid endpoint, and our right endpoint approximations. If we bumped that up to 12 rectangles, we can see our numbers changing in here. If we bumped that up to 24 rectangles, again, those numbers are changing. They're getting closer and closer to the actual area underneath the curve. But again, the more rectangles that we do, the more calculations that we have to do by hand, and then add up all of those individual areas together. If we used 48, here's the area approximations that we would get. If we used 100 or 1,000, here's those area approximations that we would get. So as we notice what's happening to our numbers, our left endpoint, which we said was going to be an underestimation, keeps getting closer and closer to 9. Our right endpoint, which we said was going to be an overestimation in this case, again, keeps getting closer and closer to 9. And our middle endpoint, which we said was going to be the best approximation, we've got 8.99999. So if we round that off, we'd get an area of 9. So if we look at what's happening, these rectangular approximation methods are all converging on an area of 9. And that's what the true area underneath this curve would be if we're looking between 0 and 3. Now again, like I said, that's a long and tedious process if we have to do all of this by hand. Imagine trying to do 1,000 rectangles by hand, calculating the width of each rectangle, calculating the height of each rectangle, doing all your multiplication, and then adding up all of those individual areas together. That'd be a pain. So what I did to actually come up with these values is I've got a program in my calculator that I can use, and I'll show you how it works. Now, in my calculator, the first thing I need to do is I'm going to go into my y equals screen, and I'm going to type in the equation that we're looking at. We're looking at y equals x squared. I've already got that typed in. So I'm going to quit out of here. Now, my program is just called the rectangular approximation method, so I hit enter, and it's going to ask me how many intervals we want to do. So for the first example, we did 6 intervals. The left endpoint, we started at 0. The right endpoint, we ended at 3. So what it's going to do is go through and run calculations to figure out the left rectangle approximation method, the middle, and the right endpoint. So we get those exact same areas that we came up with before. Now if I go back into my program and I choose that one again, and we did 1,000 intervals, the program won't actually let you go up to 1,000, but I can do 999 intervals. The left endpoint was at 0, the right endpoint was at 3, and again, it'll pretty quickly spit out each one of those approximations. So the left approximation, about 8.98, the right approximation, 9.01. In the middle, again, we can see that our middle approximation is right about 9. Now, in class, I will give each one of you this program so that you have it on your calculator to make doing all of these calculations much quicker and much easier to deal with. Now, the visual representation of this rectangular approximation method focus specifically on area, but other physical quantities can be estimated as well using this exact same method. So in this example, we're going to look at estimating the volume of a sphere that has a radius length of 4. Now, before we start thinking three-dimensionally, let's think two-dimensionally. A two-dimensional sphere is really just a circle, and if we think about the equation of a circle with a radius of 4, that would be x squared plus y squared equals 16. Now, to be able to graph this out, I want to solve this to get y alone. So the first thing I would do is subtract that x squared over to the right-hand side. So we get y squared equals 16 minus x squared, but then I would square root both sides to get rid of that squared on the y. Now we do have to remember to put the plus and the minus in front of the radical, but we'll talk about what we're going to do with that in just a little bit. I don't want to actually look at the full graph of the circle. I'm actually only going to look at the top half of my circle. So I'm mostly concerned with the positive square root of 16 minus x squared in here. Now what's going to happen to take this two-dimensional half circle in here is we're going to have to take it and three-dimensionally rotate it around our x-axis, and that's what's going to create our three-dimensional sphere. And then, as we think about breaking that sphere up into different chunks, these aren't going to be rectangular chunks. These are actually going to be cylindrical chunks. So here's what our sphere picture broken up into cylindrical chunks would look like. Now, to calculate the volume of the sphere, what we're going to do is calculate the volume of each cylinder and then just add those together. Well, if we think about the volume formula for a cylinder, that's pi r squared times the height. And what's going to be changing in here is the height of our cylinders depending on how many sub-intervals, sub-cylinders we break this sphere up into. Now we know that the radius of our sphere, if we think about our graph going from 0 out to the edge of the sphere, that's the equation, this square root of 16 minus x squared. So I'm going to fill that in for r in here. So what that's going to give me is pi times this square root of 16 minus x squared, all being squared. Now I'm going to leave the height in here for right now, but eventually when we move over into our calculator, we're not going to worry so much about that, because what we're going to be looking at is changing the height of each one of these cylinders, and that's going to give us our different approximations. So what I'm mainly concerned about is looking at squaring this square root. So I get pi, this square root and this squared are going to cancel each other out, so that's just going to be 16 minus x squared. And again, we're going to be multiplying by the height, but that height is going to change in our calculator depending on how many sub-intervals we choose to break this up into. So in my y equals screen, I'm actually going to focus on just this pi and this 16 minus x squared, and then I'll choose different numbers of subintervals to represent the height of each of those cylinders. Now before we get to our calculator, we are going to have to talk about the left endpoint and the right endpoint. This is a circle with a radius of 4, so if we start at 0 and go to the left 4, that means my left endpoint is at -4, and my right endpoint is going to be at +4. So now I'm ready to head over to my calculator and use that rectangular approximation method program that we've got. So in my y equals screen, I've already got that pi times the 16 minus x squared typed in. So I'm going to go to Program, select my rectangular approximation method. The number of intervals, let's start with 10 intervals here. The left endpoint is going to be at -4. The right endpoint is going to be at +4. And again, it'll spit out approximations for that volume. Like we talked about before, that middle approximation is going to be the most accurate. But if we want an even more accurate answer, then we need to increase the number of intervals that we're choosing. So now if we go out to 100 intervals, going between -4 and +4, I can see that the numbers are very similar, but they did change just a little bit. So we're approaching a really accurate answer in here. But I'm going to do this one more time, and I'm going to bump the number of intervals up to the max of 999, going from -4 out to +4. And if I look at the middle approximation, because that's going to be the most accurate approximation, we get an approximated volume of about 268.08 if we round that off. Now, if I want to compare that to the true volume, the volume formula for a sphere is 4/3 pi r cubed. And because we're talking about a radius of 4, I would just plug that in for the r value in here. So I'll go back to my calculator. And if I type in 4/3 times pi times 4 being raised to the third power, that's going to give me a volume of 268.08, which is about what we came up with from our middle rectangular approximation. That's going to be it for this video. Thanks for watching.